Hi everybody, this is the video for the end of week 8 on triple integrals in rectangular coordinates. Let's go ahead and get started. Okay, so the idea for triple integrals is that in the xy plane, or in the xyz coordinate system, instead of slicing something up in the rectangular xy plane, you have a three-dimensional thing and you slice it up into little cubes. And then on each cube you have a function value and you add those guys up. However, when you calculate these, you calculate them just like double integrals. It's just that you have an extra integral when you do it. So let's look at a really quick example. Okay, so we've got a cube. It has sides of length 4, and it's made of material of variable density. One corner's at the origin, okay, and the adjacent corners are on the positive x, y, and z axes. Let's come back here. So that's a 4, that's a 4, that's a 4, and this cube comes out looking like this. So there's my cube, okay, and the density at any given point is 1 plus xyz grams per cubic centimeter, and we want to find the mass. Well, you know that mass is density times volume. So we need to take this density and multiply by a volume. And so that's what we're going to do. We've got these little tiny cubes inside here. And each cube has a volume of delta x, delta y. Whoops, I got those backwards. Delta x goes along this way because this is my x-axis. So delta x, delta y is right here, and delta z is right here. Okay, so those are the coordinates for each little piece. That's your dv right here. And like always, you can put these in whatever order you want. Sometimes one order is easier than another one. Sometimes another order is easier than the first one. So you just use whatever you can do to get a nice easy setup and an easy calculation. In this case, we've got a whole lot of symmetry in this integral, so we'll just set it up. 1 plus xyz. I'll put my dx, my dy, and my dz. The x's go from 0 to 4. Since this is a cube, my limits are all going to be constants. So my first integral is to integrate with respect to x. That'll give me an x plus a 1/2 x squared yz, integrated from 0 to 4, and those are x values. And I still have a dy dz, and I still have an integral from 0 to 4 and an integral from 0 to 4. So when I put in 4 here, I'm going to get 4 plus 1/2 times 16, which is 8, yz, dy dz, integrating from 0 to 4, integrating from 0 to 4, and then now I'm down to a double integral, and I can just finish it out the way I do. So there's nothing really very exciting there. The thing that could be tricky, though, is to figure out what these shapes look like. So let's just look at these. First of all, the limits. Just like in double integrals, the outside limits always have to be constants. The middle integral can only have one variable, and that's the variable that's in the outside integral. So, for example, if we have dx, dy, and dz, these have to be constants. And the middle one, which is the y, can only have z in it. It could also be constants, of course, but it can't have x's in it, because my first integral was x's, and I plugged in numbers for my x's. If I have x's in my middle integral, then those x's come back when I've already gotten rid of them and turned them into constants. And then the inside integral can have y's and z's in it. And of course, like, doesn't have to have them both. Okay, doesn't have to have either one. They could be constants. But it can't have an x in it because if you plug in, you're trying to get rid of the x. Okay, so it can only have a y and a z. The middle one, in this case, can't have an x in it because I already got rid of the x's. It can't have a y in it because I'm trying to get rid of the y's at this stage, so it can only have z's. And the outside integral can't have any variables in it because I want to end up with a number for my constant, for my answer at the end. Let's look at one picture where we try to sketch the region of integration. Okay, we're definitely not going to integrate it because I didn't tell you what the function was here, but let's see if we can look at the region. Whoops. All right, so my first integral is z, and there's my picture. So I'm thinking about z equals 0, which is the xy plane, and z equals the square root of 1 minus x squared. And if I square both sides here, I get z squared equals 1 minus x squared, and that gives me z squared plus x squared equals 1. So I'm just going to look at the xz plane right now. Z equals 0 is the bottom of this shape, and the top of this shape is a circle. So that's in the xz plane. Now I'm going to look at dx. Dx goes from minus 1 to 1, so dx is in the entire semicircle here. And now I'm going to try to draw this in the x, y, z coordinate system, in the three-dimensional coordinate system. My y value starts at 0 and goes to 1. So here's what I've got. In the xz plane, I've got this semicircle, and the y value starts at 0 and goes out to 1. So this thing extends. And so it looks like I have a cylinder here, half of a cylinder. And I actually have the entire cylinder, not the shell. I've got the guts and everything on here. So that's how those work. Okay? All right. Take care. See you later.